Right now, as you're reading this, you're standing on the surface of a planet that's exactly 4.543 billion years old. The ground beneath your feet is solid. The air you're breathing is stable. The distance to the moon feels fixed, permanent, like it's always been this way. But 4.6 billion years ago, if you could have looked at the space where Earth exists today, you wouldn't have found a planet at all. You would have found chaos, a swirling disk of superheated gas and dust, spinning around a newborn star that had just ignited for the first time. No oceans, no continents, no life, not even solid ground. Just the raw materials of a world that didn't exist yet, scattered across millions of miles of space, waiting to become something extraordinary. This is the story of how that happened, how a cloud of debris transformed into the planet we call home, how Earth survived a collision so violent it should have destroyed it completely, how our world got its moon, its water, and the conditions that would eventually make life possible. This isn't just planetary formation. This is the most dramatic origin story in the solar system, because Earth didn't gently condense from cosmic dust. It was forged in fire, shaped by catastrophe, and born from the most spectacular collision in our planet's entire history. Welcome to TERRA. This is episode 1, Birth of a Planet. To understand how Earth formed, you first need to understand where it came from. And that story begins not 4.6 billion years ago, but even earlier, in a region of space about 26,000 light-years from the center of the Milky Way galaxy. There, in one of the galaxy's spiral arms, floated a massive cloud of gas and dust. Astronomers call structures like this a molecular cloud, but that sterile term doesn't capture what it really was. This thing was enormous, spanning dozens of light-years across, containing enough material to create thousands of stars and tens of thousands of planets. For millions of years, it just drifted through space, cold, dark, almost invisible against the background of stars. Then something happened. Maybe a nearby star exploded as a supernova, sending a shockwave rippling through the cloud. Maybe another molecular cloud collided with it. Whatever the trigger, the effect was immediate. Parts of the cloud began to collapse, not all at once but in pockets, in regions where the density was just slightly higher than average. And once those pockets started collapsing, gravity took over. The denser a region became, the more material it attracted. The more material it attracted, the denser it became. A feedback loop that accelerated over thousands of years. One of these collapsing regions, a fragment of the original cloud no more than a light-year across, would become our solar system. As it contracted, it began to spin, not because anything was pushing it, but because of physics. Conservation of angular momentum. The same principle that makes a figure skater spin faster when they pull their arms in. As the cloud shrank, it rotated faster and faster, transforming from a roughly spherical blob into a flattened disk with a dense bulge at the center. And that central bulge was getting hot. See, when you compress gas, it heats up. Every molecule that fell toward the center converted gravitational potential energy into kinetic energy, into heat. The center of the collapsing cloud reached temperatures of thousands of degrees, then tens of thousands, then hundreds of thousands. And around 4.6 billion years ago, something extraordinary happened in that superhot core. The temperature and pressure became so extreme that hydrogen atoms started fusing into helium. Nuclear fusion ignited. A star was born. Our sun flickered to life, flooding the surrounding disk with light and heat for the first time. But the sun didn't consume all the material in that original cloud. Maybe 99% of it, yes. The sun contains 99.86% of all the mass in the solar system. But that remaining fraction, that 0.14%, was still scattered across the disk surrounding the newborn star. And that leftover material, that debris, that's what would become Earth. Picture the solar nebula as it existed 4.6 billion years ago. A vast disk of gas and dust, extending billions of miles from the sun, glowing with heat from the newborn star at its center. Close to the sun, temperatures were scorching, hot enough to vaporize most materials. Only elements and compounds with extremely high melting points could exist as solids here. Metals like iron and nickel, minerals like silicates. Everything else, water, organic compounds, volatile gases, they were pushed farther out by the solar wind and radiation pressure, accumulating in the cooler outer regions of the disk. This is why the inner solar system would eventually form small rocky planets, while the outer system produced gas giants. The temperature gradient in the solar nebula determined what materials were available where. And Earth formed right at the edge of what astronomers call the frost line, close enough to the sun that it would be made primarily of rock and metal, far enough out that it could eventually acquire water, though how and when that happened is a story for later. But we're getting ahead of ourselves, because right now, 4.6 billion years ago, there is no Earth yet, just a disk of debris, and somehow that debris has to transform from scattered dust grains into a planet weighing 6 trillion kilograms. How does that happen? It starts small, microscopically small. Individual dust grains, no bigger than the particles in cigarette smoke drifting through the solar nebula. Sometimes they collide. Most of the time, they just bounce off each other. But occasionally, very occasionally, they stick. Electrostatic forces, Van der Waals forces, the same kind of molecular attraction that makes dust bunnies accumulate under your bed. Grain by grain, particle by particle, slightly larger clumps begin to form. This process is agonizingly slow at first. It might take thousands of years for a dust grain to grow to the size of a pebble. But as these particles get larger, they have more surface area. They can sweep up more material. The growth accelerates. Within about 100,000 years, the solar nebula is no longer filled with individual dust grains. It's filled with pebbles, then cobbles, then boulders, objects meters across, then tens of meters, then hundreds. And these larger bodies have enough gravity to start attracting material actively, not just waiting for random collisions. This is runaway growth. The bigger you are, the faster you grow. And it produces what scientists call planetesimals, rocky bodies ranging from kilometers to hundreds of kilometers in diameter, scattered throughout the solar nebula, all orbiting the sun in roughly the same plane. The inner solar system during this period would have been unrecognizable. Thousands, maybe millions of these planetesimals, ranging in size from mountains to moon-sized objects, all competing for the same material, all on intersecting orbits. And that meant collisions. Constant, violent, spectacular collisions. When two small planetesimals hit each other, they might stick together, merging into a larger body. Or they might shatter, breaking apart into fragments that would eventually become part of other bodies. But when large planetesimals collided, the results were catastrophic. Imagine an object the size of Mars, traveling at tens of kilometers per second, slamming into another Mars-sized body. The impact releases more energy than billions of nuclear weapons. The entire surface of both objects melts instantly, vaporizes. Material sprays out into space in vast plumes. What's left behind is a larger body, still molten, still glowing with heat, taking thousands of years to cool enough to form a solid crust again. And then that body gets hit by another planetesimal, and another, and another. This is planetary accretion. This is how Earth grew, not gently, not gradually, but through millions of years of relentless bombardment. By 4.5 billion years ago, most of the planetesimals in Earth's orbit had either been incorporated into our growing planet or ejected to other parts of the solar system. Earth at this point was maybe 90% of its current mass. Still growing, still being hit regularly, but the biggest impacts were becoming less frequent. The planet had developed a layered structure. The heaviest elements, iron and nickel, had sunk to the center, forming a dense metallic core. Lighter silicate rocks had risen to form a mantle and crust. The surface was still molten, still glowing red hot from the constant impacts and the heat of formation. But Earth was beginning to look like a planet. Then came the impact that would define our world forever. The collision that would give Earth its moon and fundamentally alter the course of planetary evolution. Because somewhere else in the inner solar system, another planet had formed. Scientists call it TERRA, named after the Greek Titan who was the mother of the moon goddess Selene, and TERRA was on a collision course with Earth. We don't know exactly how big TERRA was. Estimates range from Mars-sized, about half Earth's diameter, to even larger. But we know it existed because of what it left behind. The moon, and the specific chemistry of lunar rocks tells us this wasn't just a grazing blow. This was a direct hit, the most catastrophic collision Earth has ever experienced. Around 4.5 billion years ago, maybe 50 to 100 million years after Earth first formed, Theia entered Earth's orbital space. Maybe the two planets had been gravitationally influencing each other for thousands of years, their orbits gradually converging. Maybe Theia was knocked into Earth's path by interactions with other planetesimals. We'll probably never know the exact mechanics, but the result was inevitable. Two planets, each thousands of kilometers in diameter, each traveling at orbital velocities of tens of kilometers per second, on trajectories that intersected. The moment of impact lasted less than a second, but that single second changed everything. Theia struck Earth at an oblique angle, not head-on, but not quite a grazing blow either. Something close to 45 degrees. And when two planet-sized objects collide at those speeds, matter doesn't behave like solid rock anymore. It behaves like fluid, like liquid. The entire impact zone vaporized instantly. Not just melted, vaporized. Rock turned to gas in the fraction of a second it took for the two bodies to interpenetrate. The energy released was beyond comprehension. More than all the earthquakes Earth has experienced in its entire history combined. More than every volcanic eruption. More than every meteor impact. All of that energy concentrated into a single cataclysmic moment. The shockwave from the impact propagated through both planets, triggering seismic events that would have torn any existing surface, features apart. But there were no surface features, because within minutes of the impact, the entire surface of Earth was an ocean of molten rock. Theia's iron core, denser than the surrounding material, punched through Earth's mantle like a bullet through water. It didn't stop, couldn't stop. Momentum carried it down toward Earth's core, where it merged with our planet's existing metallic center, adding its mass to what would become Earth's unified core. This is why Earth's core is disproportionately large for a planet our size. We didn't just accrete our iron from planetesimals over millions of years. We inherited a substantial portion of it from Theia, delivered in a single catastrophic merger. But Theia's mantle, the rocky material surrounding its core, didn't sink. When it hit Earth's mantle, The collision was so violent that enormous quantities of material were ejected into space, not just from TERRA, from Earth too. The impact excavated a substantial portion of our planet's outer layers, hurling thousands of cubic kilometers of vaporized and molten rock into orbit. Some of this material had enough velocity to escape Earth's gravity entirely, lost to space forever. But most of it remained bound to Earth, spreading out into a vast disk of debris circling our battered planet. In the hours and days after the impact, this disk would have been spectacular if anyone had been there to see it. A ring system more extensive than Saturn's, composed not of ice, but of molten rock and vaporized silicates, glowing orange and red against the blackness of space. The disk was unstable. Material within it was colliding constantly, some fragments merging, others shattering. But gravity was working on it, pulling material together, and within months or years the debris began to coalesce. The moon formed quickly by geological standards. Within a few thousand years of the impact, maybe within a century, most of the material in the debris disk had accumulated into a single, large body, our moon. And it was much, much closer to Earth than it is today, maybe only 15,000 miles away, compared to the current distance of about 239,000 miles from Earth's surface. If you could have stood on the molten hellscape that existed in those first years, the moon would have dominated the sky, appearing 15 times larger than it does today, looming overhead like an impossible sphere of grey rock. And the moon was hot, still molten from the energy of its formation. Its entire surface was an ocean of magma, glowing red, slowly cooling over thousands of years as it radiated heat into space. Earth was the same. The impact had reset our planet's geological clock, remelting the surface, erasing whatever structure had developed during the first 50 million years of accretion. For thousands of years after the TERRA impact, Earth and Moon orbited each other as twin spheres of molten rock, locked in a gravitational embrace that would define both worlds forever. But here's what makes the Moon so important. It wasn't just a cosmic accident. The Moon stabilized Earth's rotation. Without it, our planet's axial tilt would vary chaotically over millions of years, making climate wildly unstable and probably preventing complex life from evolving. The Moon's gravity created tides, and those tides would eventually play a crucial role in the chemistry of Earth's early oceans and possibly the origin of life. The Moon slowed Earth's rotation through tidal friction, transforming a planet that initially rotated once every 5 hours into one with 24-hour days. Everything about Earth that makes it habitable can be traced back in some way to the TERRA impact. We are the product of catastrophe, the result of a collision that should have destroyed our world, but instead created the conditions for everything that followed. So here we are, 4.5 billion years ago. Earth has reached essentially its final mass. The Moon orbits overhead, still glowing with the heat of formation. The age of giant impacts is ending. Most of the large planetesimals have been swept up. The solar system is beginning to settle into the configuration we recognize today. But Earth is still a hellscape. The surface is molten. The atmosphere, if you can even call it that, is a toxic mixture of vaporized rock and whatever gases manage to avoid being blasted into space by the impact. There are no oceans, no continents, no life. Just a ball of molten rock slowly, very slowly, beginning to cool. And that cooling process, that transition from a molten world to a planet with a solid surface, with oceans, with an atmosphere that could support life, that's a story that takes hundreds of millions of years to unfold. A story of constant bombardment by asteroids and comets, of volcanic eruptions that would dwarf anything in recorded history, of an atmosphere so poisonous it would kill any modern organism instantly, of a world being forged in fire, preparing for the moment when the first simple molecules would somehow organize themselves into something that could replicate, could evolve, could eventually lead to you, standing here billions of years later, trying to understand how all of this happened. Earth's birth was violent, chaotic, forged in collision and fire. But that violence created something extraordinary. A planet perfectly positioned, perfectly sized, with a stabilizing moon and the chemical ingredients necessary for life. We exist because of the TERRA impact, because of millions of years of planetesimal collisions, because of the specific conditions that existed in the solar nebula 4.6 billion years ago. Every atom in your body was forged in the heart of a dying star billions of years before Earth existed, then scattered into space by a supernova explosion, then incorporated into the solar nebula, then swept up by planetesimals, then merged into Earth through countless collisions. You are made of recycled stardust, organized by gravity and heat into a planet, and then organized again by chemistry and biology into consciousness capable of looking back and understanding the journey. That's the miracle of Earth. Not that it formed, planets form all the time around stars throughout the galaxy, but that it formed in exactly the right way, at exactly the right distance, with exactly the right composition and moon to become a world where life could emerge and thrive, and eventually build civilizations that could tell this story. But we've only just begun, because the Earth that emerged from the TERRA impact, that molten ball of rock cooling in space, was nothing like the world we know today. What happened next was 500 million years of transformation so dramatic it would make the TERRA impact look like the opening act. Next time on TERRA, we descend into hell on Earth. The surface is an ocean of magma. The sky rains molten rock. Asteroids the size of mountains slam into the planet daily. And somewhere in that chaos, water arrives. Oceans begin to form. And the stage is set for the emergence of the first continents. The planet is about to transform from a ball of molten rock into something that could eventually support life. If you want to see that transformation, subscribe to this channel. Because the story of Earth is just beginning, and it only gets more dramatic from here.